just take a peek at the agenda, and we are gonna go into each unit, so I'll keep it short. But this unit is broken into 3 tasks. And actually, it even makes sense to maybe hop over. So we're just really just gonna, the agenda is to take each of those tasks, and we end with a breakout room for each of those and save a little bit of time for questions at the end. Just to flash it up, here is the idea capture tool that's in the chat. So if you don't have a chance, those parking lot questions, we'll make sure to answer while you're in breakout room. So we just try to get to it. And as always, this has been a great year. People have really left some great resources. So if you do have great videos or really any resource, we're always, this was collaboratively developed by teachers. So if you're willing to share those, we'd love those, and just want to make it easy as possible.
You stuck, Doug?
Was that a question? Oh yeah, no problem.
Oh, sorry.
Oh yeah, no problem. Yep. So parking lot questions, suggested improvements. I'm going to close that for now. I got it on another tab. Here's that course attendance. And of course, this would be the webinar unit 7. All right. And so here we go. This unit is unit 7. And this is really meant, these are 3 separate. They do work well. They're all, astronomy based. However, just so you have this option that you might have, and we're getting close to the end of the year now, so you'll probably do it all together, which is the best way to do it. But if you do, just for the future, note that we had a couple days before winter break, and we didn't want to start a new unit. And so we actually did Halley's Comet. So these are modular. They can be dropped in. So here is Halley's Comet. And of course, that's getting at Newton's universal law of gravity. And you do see it mentions Coulomb's law as well, because they're both inverse square laws. That'll be the first one we talk about. Then we have the next one with looking at mathematical and computational representations of orbiting objects. So very great one that really builds on some of the work we did in unit 3. So you'll notice that these have a optimal placement. And yep, so it'd be nice if you've covered energy already before doing that one. And then the construct an explanation of the Big Bang Theory. And that is it's a great one. We've just gotten a lot of positive feedback generally on all of them, but we always like critiques. That is how we get it better too. So when you find something you don't like, please do share that too. But this one is a stations activity, really high interest. And that one is loaded with great videos, and we'll show a couple of those. All right, so that's the overview of the unit. It doesn't have the storyline and the engineering project like the other units, because of this modular nature.
And I think Bradford, you might have mentioned, but just as a aside, that there is a note on optimal placement about where the best placement. Of course, these can all be at the end of the year and together as one big chunk, or like Bradford did in his classroom this year while I was out on leave. He did a one chunk, the Halley's Comet, already this year, and he'll come back to other sections. So intentionally, it is modular for just adding a little bit of flexibility.
Great. Okay, so let's dive into. Actually, now I do want to maybe go back to the agenda to give you a sense of just people appreciate what's going to happen. So here we are, right about here, highlighting the task. And these ones are, this is great. This one is nice that if many people are probably doing unit 6 before this, which had the sine wave, right? So for the whole year, we've been working on horizontal line, proportional, quadratic, inversely proportional. And we stuck with it long enough that really almost all students, I really want to say almost all students, have gotten familiar with those. They have gained proficiency. And, you know, just like we say with so many talk structures, we want to stay with things long enough that students have a chance to get good. But also, you want to mix things up to keep it fresh. And, you know, it's getting towards the end of the year. So we want them to realize it's not just those four patterns. The universe is big and complicated. So in unit 6, we introduced sinusoidal with the solar array lab. And here, it's also nice that we have inverse square. So we're introducing a new mathematical pattern. You know, we don't ask them to like solve for the square root of distances. That is not called for in the evidence statements. And certainly that's like, if you have students that's a great challenge, that's awesome. But you can also save that for a senior level physics course, which will almost certainly have that. And then really here is, and we're going to show the slide, so maybe I'll just say it and then wait till we show the slides. But, you know, there are students that don't necessarily love physics, but a lot of people like astronomy, right? I mean, just that the visual nature of it, that the awe. And maybe it's worth saying that, you know, some students, you know, one of the critiques that Neil deGrasse Tyson talks about with astrophysics, that astronomy can make students feel small and insignificant. And we don't want that. But in any case, that's a chance for you to, and this whole unit and all of the astronomy units are just that thing that the universe is amazing and beautiful, and there's a lot there. But note that, you know, sometimes when students see that, that is a real thing that people, astronomers and astrophysicists here, is an unexpected consequence or maybe surprising to people that just love everything about the universe. All right, and then it's really important. This is one of, in physics, I mean, chemistry has a lot more examples of these, and physics does too, but this is one of the best places to get at the cross-cutting concept, scale, proportionality, and quantity. That is just loaded in this unit. So we want to do that in a couple other places, but this is one of the best places in the whole year to get at that cross-cutting concept. Okay, so now let's show how are we building common background? I'll throw it over to Matt. How are we building common background and achieving the things that I just mentioned? So we're going to jump into the slides.
Yeah, so just in the slides, starting with the phenomena. Halley's comet is only regularly visible comet to the naked eye, and there's a good story about like this was named after somebody who was the first person to recognize that it was that it was the same comet seen every time, but it's been seen for uh, hundreds or thousands of years each time, and so there is just some background on like here's some you know, a variety of different photographs. Bradford, if you go to the next slide, probably won't show it, but there's a video that talks about you know, connecting the comet to different times in history. Recently, on the next slide, if you don't mind, just looking at landing on a comet or asteroid, and just kind of bringing up those ideas, and there's lots of conversations about like the difference between comets, asteroids, meteors, and looking at this phenomena of this comet as its elliptical orbit is continuing over time. So, but if you skip 2 slides here, just yeah, maybe one more. I don't know if this one's worth showing, but yeah, just looking at some of the the earliest photographs of when it's close. There's other early photos of it. One of the best photos is ahead here in the slides. Bradford, thanks. Yeah, some of the best photos, so still early photographs of it. But this is this comet that's continuing on, and so we start with this as our phenomena and start to look at that elliptical orbit as it's kind of moving around in space. And but for I'll pass it to you to kind of finish the slides, but then look at the desmos that's associated with it.
Yep, awesome. And then great, we have someone joining, so we got to repost.
Yeah,
Awesome, thank you. Yeah, and then here 1986 it returns, so of course better telescopes and are able to get better images. And then in 2003, so it's way out there near the orbit of Uranus, and really it's just that darker patch right there in the center. So they did take a picture, and of course, as it gets away from the sun, increasingly hard to see it. And then so here's a little bit of a timestamp of that elliptical orbit. So 2003, and of course now at 2024, really one of the farthest in its elliptical orbit. I was going to say apogee. I'm not sure. Awesome. So here's just a couple more slides, that just show that Halley's Comet is pretty unique in that, highly elliptical orbit when a lot of the other major planets all have very near circular orbits. And of course, Pluto doesn't, and it's a minor planet. And another thing that's cool is it's retrograde. It's spinning the opposite direction, and it's not in the solar plane. So most of the planets, of course, with how they formed, are in the solar plane. And then I think we got one more. So here's a side view. So you can just see that Halley's Comet really does seem to be a little bit different. And students, of course, ask about Pluto, and that's right there, and that's fun to talk about. Great. And then just one last thing is our solar plane is out of the galactic plane. And of course, you can, with the night sky, if you ever get a chance to see the Milky Way, you can see it doesn't line up with, the equator or the solar plane. But of course, the Earth's tilted a little bit. So even the equator is tilted to the solar plane. But with all of that, it's just kind of neat. So, you'll get a couple students that kind of just have either they haven't thought about it, or they just kind of think because the solar system's flat, that the galaxy's flat, and that everything is sort of flat. And really, obviously, we live in a three-dimensional universe, and there's a lot of planes that don't all intersect. So that's just a light touch of, that's a chance to have awe, right? Like that's not intimidating. There's lots of realizations happening. Students have questions, and that's exactly what we want. And then Matt hinted at it, so we'll dive in. So this is a little bit more of the experimental, or the really graph analysis is what we're going for here. So here's that hypothesis. What is the effect of gravity? No surprise, as you get further from the sun. Okay, and then, like we have done with Newton's second law, we are data mining. So they, especially with astronomy, there's giant data sets out there. And so they really just have the question, how does distance affect gravity? But they're given way more columns than they need. So they really just need to highlight two of these. And okay, distance from the sun. So we want that. That's our independent variable. And maybe they write IV and then how does that affect? Well, there's all these different things, but really we just want this. And you might even color code it. Actually, we're doing a design lab right now where they're making a visual procedure and color coding all of that. Okay, excellent. But in any case, and dependent variable, good stuff. So how does distance affect gravity? No surprise that we used to have to manually enter the data. They never look, they don't realize this, but the data is already imported just to save them time. That's not mission critical. We hopefully by this point in the year know that they could enter that. And so we just get them there. And then of course we are going to find the mathematical model. And proportional, that just doesn't fit. Actually, I'm kind of saying some of this for people that are totally new to the patterns, but I know that we're gonna run out of time. So, all right. And so they have to, of course, fit this, and it just doesn't make sense to have that red, the quadratic pattern going up. That doesn't make sense. The green is the one they're familiar with, inversely proportional, but you just can't get it to work. And like we've even had teachers, and including myself, you just vaguely think of inversely proportional and inverse square. Like they're both kind of down and over, down swoopy, but they are very different functions. And you can just see that, you can really see that the purple, how inverse square is different than inversely proportional. And the proof is in the pudding. You can only make the purple line act like the data we see with Halley's Comet going around the sun. So the purple works and the green doesn't. There's just no way. If I lower it to get to some points, it's just going to completely miss these. And we really want students to see that. So if they delete it too quickly, you'll just have students that think, oh, that's inversely proportional. That's not inversely proportional. Look, our function is d squared. So I highlight that to say that is why we think it's inversely proportional. And students might want another explanation, and that's great to explore those. But the number one explanation is it is that only inverse square fits the data. And so if they miss that, there's no explanation that's going to then make it make sense. So don't miss that. They might need stuff in addition to that. There's some clever thinking about why it's inverse square. Okay, but yep. So I will just move on. Card sort, right? Students have gotten really good. We had the student talk PLC last night, and it was really cool because people were saying, this time of year, students are really, for some classes, they're finally getting data discussions. That is really awesome. And now we got a new pattern, inverse square, that can be intimidating, but a neat thing that I'll say is we've heard it, I've seen it with my own students, and I've heard it from other teachers. That's really the combo of quadratic and inversely proportional. So something's in this world when you double the distance. Oh, I have my thing right here. Something's in this world when you double the distance, two things happen. It gets twice as wide, twice as tall. Oh, so the output quadruples. Well, gravity's like that. If you get twice as far, it doesn't get twice as small. It gets 4 times as small because there's two things happening. Okay, so that's good stuff, but the card sort also helps them through that. All right, so then we want to show this. This is a FET that we'll return to a couple times. So that's a nice little simulation. They can move that around. They can click on it and just look and check that quadratic nature. Look at the force, doubling the force. Did it make it twice as small or 4 times as small? Okay, all good stuff. But here, I'm not going to show every slide actually. So in any case, they're just pointing out what objects seem to affect it, getting them to write a little bit. We've hit the main part of the universal law, but there is some things in the evidence statement. So I don't want to read every one of these slides to you. So in any case, why you might ask, why are some of these details here? It is straight from the evidence statements and the next generation science standards. It says they need to do some calculations. And that's unfortunate in a little bit because those are some crazy numbers. But that is, I try to emphasize that we haven't had students deal with 10 to the negative 11th a lot. That's not many other places in the NGSS for the physics standards, but that's good. That's a good lead up to chemistry. They're going to see a lot of that in the following year. So, it is a good thing, and know to expect some groans in those units. But in any case, that's straight out of the evidence statement. So really did feel we needed to put that in there. And this can be, you'll have to think about, it's worth showing here to think about, is that something that they're going to, model guide step aside? Do you do slide 19 and then have them do slide 10 in groups and then really try one individually? Anyways, there is a cool little thing in here that once you enter a number and you hit play, yeah, my number was too close. Let's just say if you thought gravity on the sun was the same as gravity on Earth, you would say 10, meters per second squared, or this is a lot, and I didn't mention this till now. the same units, 10 newtons per kilogram. That's another great way to talk about the strength of gravity. The slides do that. I did not. So I'll just say that that's the same unit as meters per second squared, if you haven't thought about that. A lot of textbooks are switching to this. A lot of physics education research says using meters per second squared for the strength of gravity is weird because so many objects we see are not in free fall. So what is always true with gravity? If on the surface of the earth, it pulls 10 newtons for every kilogram of matter that you have. And if you have a 2 kilogram book, okay, well, each kilogram of that book is getting pulled 10. So if you have a 2 kilogram book, it's going to get pulled 20 newtons. 2 kilograms times 10 newtons per kilogram. All right. Sorry about that aside. I know that doesn't that's a lot of information with the slide that's not even about that. But in any case, that's a unit that, again, physics education research says is a much better way for students to think about it. But they might have been taught in middle school, meters per second squared, which is also good. We just know that if you have the only force on an object is gravity and you drop it, it will also accelerate, roughly speaking, 10 meters per second squared. Of course, 9.8, or there's little precision that you may want to decide. But just for fun, after students do a calculation and they put the number in, they hit play, and you can kind of see the real jumper and the ghost jumper. So I'll get even more mismatched. It's unfortunate that I'm on the sun maybe right now because the sun's so powerful. Yeah, see, there's the real jumper, the white. That's the number I put in, the solid jumper. There's a 1, and you saw the ghost, which is what really happens. So in a sense, they can sort of this is to give them feedback on did they do the calculation correct. So 1 was not correct. I should not see the ghost and the real jumper. So in any case, I just happen to know from doing this enough roughly what the sun is, but I'll go to 22 and hit play. Oh, I saw the ghost. And so I'm close, but of course they should actually put this in a calculator. We want them to, one time, and most students will need help. You got some math superstars that will be like, think this is fun, but a lot of other students, they're going to need to find, how do I put a number like this into my calculator? So just a great last little lesson to do before they go to chemistry. In any case, it's actually, I don't remember well enough off the top of my head. I know it's around 25 or 30, but I'll just do 28 and probably call it good. Okay, I still saw the ghost, so I got to get it right. But anyways, that's some nice little visual feedback for them if they did the calculation correctly for figuring out the gravitational field strength. Nice. Okay. So here's just a nice little question, and it's really heartwarming, actually. So just ask them to, isn't that amazing that the same gravity that keeps you close to the surface of the earth is the same force that keeps the earth going around the sun, and the same force that keeps Jupiter going around the sun, and the sun going around our Milky Way galaxy. So it's really fun. Some students really say some neat things, so we just wanted to have a space for that. And then just to wrap this up, there's that extension, because remember in the performance expectation, they're really meant to see a similarity between gravity and Coulomb's law. So there's that return simulation. They can return to that same simulation and go, oh my gosh, it's basically the same thing. Of course, the two big differences are the size of the forces involved, and that electricity and magnetism can repel, right? Gravity is always attractive, but electromagnetism can attract or repel. All right, so that was a deeper, that's probably about the right fit. That's an overview of the Halley's Comet task. And that's really aiming for like 2 days. There, of course, is some extensions you can do, and we have some listed down here if you do have more time, but really trying to, with the importance of Unit 6, making sure if you're short on time, this is 2 days, so that usually can fit if you do have that time. I'll just wrap up myself, turn it over to Matt to see any comments or something that I missed on the main thrust, and then we'll talk about go into one of the extension applications.
Yeah, no, I was just gonna kind of lead into that extension application that there are so many interesting uh astronomy and space science videos out there that we're going to show you a select few and some of the shorter ones, but they're just so many cool applications. And so one of those cool applications that I was surprised to learn about is on a video that we have um, here, and just you the scale in the sky. And so this is a just a minute and 45-second video just to kind of get you a taste of some of the other cool videos that are and resources that are there. And then after this, we'll have like a quick 5-minute breakout room to just check in with teachers around the state and some around the nation. But Bradford, if you want to show this video here.
Gravity. It's everywhere. It's the force that keeps our feet on the ground and the moon orbiting Earth. But where does it come from? Mass. That's simply the amount of stuff that makes up an object. The more mass something has, the more gravity it has. Earth's gravity is constantly changing because something with a lot of mass is moving around all the time. What's moving? Water and ice. If you've ever picked up a bucket of water, you felt just how much mass it has. It creates a lot of gravity. Using satellites, NASA can measure Earth's gravity like a scale in the sky. By comparing one month to the next, we can track where the water and ice is going. Weaker gravity means there's less water in that spot. This can tell us where a glacier is melting or a severe drought is drying up lakes. And stronger gravity? More water, such as in the rainforest in the Amazon. Our scale in the sky even lets us measure water deep underground. Knowing where the water and ice is moving helps us improve weather models, forecast droughts, floods, and wildfires. It also helps us get water where people need it. Measuring gravity from space helps NASA better understand the entire water cycle here on Earth. And that can come in handy next time you want a glass of the stuff.
Just kind of a cool application of looking at the force of gravity of the water and seeing where the water is going, changing, and using that to help inform models. Again, there's lots of cool resources like this that we found and curated and have been shared with us. So lots of cool connections for things like that. We're pretty close here on our just a quick discussion in breakout rooms. Yeah, Bradford, it looks like you have that copied. So we're going to just spend a 5 minutes in a breakout room and just have some time to chat and just see, like, where do you see placing these modular tasks, or would you prefer to like save them to the end and preserve them as a full unit? Just kind of thinking through how you might use tasks like this. Of course, you've only seen one. There's 2 more to come as we are presenting here. We are going to, again, just have a 5-minute breakout room, and then they should automatically close right at the end of the time, and we'll see you back here after about 5 minutes here. All right. So again, the task is, where do you see placing the modular tasks, or would you rather preserve them as a full unit? Again. Yeah, so we hit the first module there, and our second module is around the idea of orbital motion. And we want to bridge this back to some familiar concepts that we've been using since the bungee jump unit in energy bar charts. So we're going to be using an energy explanation looking at orbital systems. And so for this activity, there's going to be lots of simulations that they're going to be using, and one of those is going to be around kind of connecting the energy skate park that they did early in the year to orbital motion, and looking at it on different, looking at energy, kinetic energy, and gravitational potential energy on different scales. And so wanted to just say, like, this is ideally placed, or really needs to be placed after um, uh, an energy unit, unit 3. It can be right after, or it could be at the end of the year, but it really does lean heavily on looking at energy explanations there. And so with that, I'll hand it off to Bradford to talk a little bit about some of the demos and things that we do to introduce this.
Great, thank you. Yeah, really fun way to start. I'll just show again the agenda here. Really fun way to start the unit, and that ties gravity and orbits together. Of course, gravity is why things go in orbit in our solar system. Okay, so this, I'll just play a few. This is a longer video, and yeah, rolling it. And this is a very simple apparatus, just fabric. You got to kind of get the right fabric. Paper clips, those large ones though, and like a hula hoop and some stools. But there is one that you can buy that's all like pre-made. That is in our supply list, but in any case. So we strongly suggest actually having um, a real setup. So this is just a video to show it and give you a feel in the webinar for what's going on. And there's just lots of questions, and they notice, I was trying to find one where, yeah, here, like this is a fun thing to do. If everyone had, you know, we have tons of ball bearings from some of our other supply lists, and you see that collisions and things fall in, things stay out, and you know, you try to get a circular orbit versus an elliptical orbit, and oh, when it's in an elliptical orbit, it's fast when it's near here, and then it slows down as it goes up. There's just so much, you know, the phenomena is rich. And, you know, in the astronomy unit, where a lot of the rest of it is going to be simulations and stuff, this is just an excellent way that we strongly encourage you to. It does take a little bit of effort. That's why I thought the encouragement. Material list, though, does have a pre-made one that, you know, you do have to have a budget for. It is a little bit pricey, a couple $100. But you can make this with just like $20. All right. So then, just as Matt said, this is a Desmos classroom that was made. And again, we want that cross-cutting concept energy. This is a beautiful connection of, you know, energy is just, it's so obvious why energy is both a performance expectation and a cross-cutting concept. That really is the unifying tool that we want them to have when they first look at almost any system, including when they go to chemistry, when they go to biology. So just again, nice, you know, unit 7 again, having those things. And just like they did in unit 7, okay, at this point, it has just a little bit of kinetic energy because it's maybe moving. To me, it looks kind of stationary. I just want to show you the bar charts, the EK, the EG, and the total. And then at the end, at another position, position 4, that's right here. Okay, it's starting to slow down, but it has more energy than it did there, although it's kind of at the end, so maybe the EK was 0. And, you know, the thing here is, oh, it has the same total energy. So we can figure out, again, it's not as high, so that makes sense that the bar charts is not as high. So just showing that strong connection. Now I'm going to jump to slide 9. And then they do the same thing. And again, if they had done that with the demonstration, a lot of students expect that. And again, we want to walk the triangle. We want them to live a real life experience and then use a graphical representation to capture what's, I'm not trying to do these accurately. And then they have a graphical representation. And of course, ultimately, we even want them to have a mathematical explanation. And these slides bring them through that. And just, again, want to emphasize, if you got that demo table, they can be going from the real life. And when students are talking about, oh yeah, does it really get going faster at B? Yeah, walk over to that demo and roll that ball and you will just, it's rolling downhill, right? Like we know we have that intuition with the skateboarder that'll be going faster. And if you fall towards the earth, and hey, if you are going really fast when you're near the earth sideways, well, then you're going to get the distance you're going to get from the center of the earth is going to get farther. And so they're already trying to, it totally makes sense why it's an elliptical orbit. If you speed up, and if you're far, yeah, well, I'm catching myself talking really fast. So I'll just slow down and re-emphasize that when you're at position B, you have very little, sorry, you have a lot of kinetic energy, very little gravitational. You're going really fast, so you are going to move away from the center of the earth. When you get to A, you've slowed down now. Your kinetic energy is really low. You still have some sideways speed, but what's going to happen? Of course, you're going to start falling towards the earth and not have enough sideways speed to maintain that radius of orbit. So lots of interconnecting things that really appropriate for freshmen to wonder about, engage, and connect. Okay. And then here is that activity. I do want to kind of just show this with teacher Desmos. We've done a few of these, but maybe if you haven't done it, you will make your own class copy here. So that's that teacher Desmos. Once you make it, you will need to assign it to your class. And I'm in a different Google identity than my own class, my school at one. So I don't have classes set up in this Google identity. But in any case, here, this gives you that overview of all of them. I don't want to actually show it much, but there is, we really want students understanding orbits in terms of energy, the cross-cutting concept, it's intuitive, but the evidence statements does call out Kepler's laws. So we actually want them to go into Kepler's laws, not to memorize them, but to say why it makes sense. Oh my gosh, why is it sweep out or equal areas? Kepler figured that out empirically, but we want them to use energy. And it really is tied to what we just said. So you can see how that leads together. When you're close to Earth, the base of the triangle is very short, but when you're close to Earth, you have a lot of kinetic energy. So what did I say, the base? I meant the height. But the base, because you're moving fast, is going to be wide. And then, of course, over here at one day, when you're far from the Earth, the height of that triangle is very long. The radius to the center of the Earth is very long. But you don't have the same kinetic energy, so you don't move, making the base of that triangle shorter. And of course, it turns out they are actually roughly perfectly equal. All right, so that is the sorry, I closed that and that brought this up, which I didn't want to talk about quite yet. That just shows you the connection of what Matt said about energy analysis, that cross-cutting concept, bar charts, stick with something long enough that they build competency. We had those bar charts with the bungee jump, bar charts when we analyzed wind turbines in Unit 6, and we got bar charts to understand orbits so that students actually go into Kepler's law, not in memorizing them, but actually trying to explain them in terms of using the tools of science, energy bar charts. We got a lot of other fun things, and I'll hand it back to Matt to talk about some of the extensions that you can do with orbital motion.
Yeah. Before I do, Bradford, can you click on the gravity and orbits fit there just in the middle of the screen? Yeah. So a lot of this Desmos activity is around just this FET. And so just if you're not familiar with it, just does a good job modeling planetary systems. And so students will interact with this with the Desmos classroom activity, and use those together in conjunction with their understanding of energy to look at systems. And so I wanted to show this because we're going to show some others simulations as well that are just kind of fun simulations, but this one does a good job of being pretty clear, pretty foolproof, and just giving them a good idea of what's going on with orbital motion and seeing those. They make some stable orbits, they make some unstable orbits, and kind of are guided through with that. The next, like towards the end of the slides, there's just a couple of, you know, extra um, extensions that they can do. One of them was the one that Bradford was clicking on earlier. This is just like a chaotic planets, random planetary motion generator. And so one for them to have fun, and they can make their own orbits, and they can change masses and see how that changes the system, things like that. So this is one that's just kind of fun for them uh, to look at and do. The next one, um, this one's a little bit harder for them to do, and it's essentially um, making a small universe, and it really gets to the connection that we had at the beginning with the demo of the fabric that was bending, and this does a this one does the best job that I've seen of a simulation that shows um, that bending of the space-time as you make a mass. It's a little bit harder for students to work with, and actually they're better at it than I am because they can use their touch screen and they flick the planets. And then it does a good job of coming up with like some observations that come up as they're playing around with it. So it's just another kind of fun extension. Students are all, oh, look what I did, and you can make some cool different systems with this, and students just have fun uh, playing while they're learning those things. So those are just some kind of cool extensions. And then Bradford, if you don't mind going to the next slide, we want to come back and hark back to this, and this is a good one that you know, what would the energy bar charts look at different points? We're looking back at Halley's Comet, and we've already kind of foreshadowed this, that you can look at that energy, and actually right now, 2024, Halley's Comet's way out, and it's moving pretty slowly. Got lots of gravitational potential energy, not much kinetic energy. And then as it falls in here in what, 40 years, um, it'll be back and doing that. And you can also kind of see that, like kind of like that image, just because you can see from the dot, if you were doing a dot diagram of like how those dots are so close, that how much slower it is moving. So just kind of another connection to something that we had done earlier there. Good. Let's see. I think, yeah.
Yeah, excellent. And those simulations also, you know, just how like the Earth is going around the sun, which is going around the Milky Way. So some of those traces and simulations, students are just primed. And when you know that they're there, when a student brings it up, you're like, that's awesome. And we have a simulation coming up that you can sort of trace that and see that complexity. Good. And here, this is that description I was just saying. So you can see that the slides will prompt you to have students consider that. Just checking over the agenda, make sure we hit yep.
There's
Back.
that one last tab that up there on the right.
Yeah.
Yeah.
Just because it is so relevant, right? Like the Artemis missions are going on, and yeah, I guess the stage 2 astronauts have been selected, although it does look like they're going to postpone that launch. But that's going to happen in their high school time. So just a neat one. I don't remember if we were showing this one or just.
Yeah. I'll just say this one's a neat one, and it's a bit longer, so I don't think we'll show it. It does a good job kind of talking about the problem of, you know, going back to the moon, and talking about like using elliptical orbits, and has some cool animations along with that. So that's just one thing that you know, we show to just give some extra access to these ideas, see what NASA's doing with this here.
And current events, yeah. Excellent. So let's hop back to, okay. Yep, we have, yeah, just another chance to connect with your colleagues, process this, talk a little bit about it. There wasn't anything in the idea capture tool, and no need to, but if you do have a question, we'll try to answer that. But here is, what's getting you excited about space and the universe, or, just something that, sometimes students don't always love physics, but, is this a chance, especially if you do it at the end of the year or this time of spring, right? Like, just a chance. Do you see a chance to pull a student in who maybe hasn't been excited by other projects? So, if you think about that, you can bring that intentionality and try to make that happen. So I want to give you a chance to talk about that with your colleagues. And yeah, Matt already got in the breakout room. So
Yeah.
open that breakout room.
All right. Yeah, I'll open that up, and we'll see you back here in about 5 minutes.
And then we want to pause. Bryce, are you there? Thanks. Welcome back. I lost my just unit 7. Get another one open. All right, so just a quick review to bring you back. We had Halley's comet task, the orbital motion task, and then really that construct an explanation of the Big Bang based on astronomical evidence of light spectra, motion of distant galaxies, and the composition of matter in the universe. That last one, it sounds like just another one. That is sophisticated. So, but you'll see. And so I'll just say you'll see why the stations were picked as they were. This, just want to lead with this one, just have gotten a lot of positive feedback. So really a fun unit that, gets to talk about some of the wild stuff with our universe. We were going to start with a video, and we've had it said, including myself, like like you gotta actually, we put it in the agenda that dark energy, not really well understood, and I was going to go back to the agenda, and there's tantalizing hint, but that maybe dark energy isn't working like we thought. So that is not settled, right? Like, this is a current event. This is a understanding that is still emerging. So that is really fun and something that, you got to stay up to date on. So we do want to watch this video though, because it does just show how different the universe is from what you might sort of just expect it to be, even after like, oh, it's several billion years old, and so star might be just several billion light years away. Okay, well, I'm going to play the video because I think the video does a better job.
There was a time when the universe was expanding so rapidly that parts of it were moving apart from each other faster than the speed of light. That time is right now. A lot of people make a big deal out of the fact that during inflation, right after our universe burst into existence, the whole universe was expanding faster than light. Now, while that is true, it kind of implies that the universe doesn't normally do that, and it does. I mean, if you pick 2 points far enough apart in our universe, you can always find ones that are moving apart from each other faster than light. That is simply due to all of the expanding space in between. So our universe is now and has always been expanding faster than the speed of light. But doesn't this violate Einstein's special theory of relativity that says nothing should be able to move faster than light? Actually, no. Relativity says nothing can move through space faster than light, but that doesn't stop space itself from expanding however it likes. Now, it was Hubble in the late 1920s who made the observations of the night sky, which led us to see that our universe is expanding. The further out in space he looked, the faster the objects were moving away from us. So imagine a point so far out there that the average recession velocity is the speed of light. I mean, if you think about it, it's going to be the same distance in every direction. So that would form a sphere, which we call the Hubble sphere. Everything beyond that sphere is moving away from us faster than the speed of light. So common sense would say we would never be able to see the light from those objects because of how fast they're moving away from us. But in fact, this is not true. We can see those objects. To understand how this could work, picture a galaxy beyond our Hubble sphere. It's receding faster than light. It's in a superluminal region of space from our perspective. So any light that emits in our direction will actually be moving away from us as time goes on. Well, that doesn't sound very promising. But due to the accelerating expansion of space, our Hubble sphere is actually getting bigger. And if it gets bigger faster than that light can get away, then at some point that light is going to travel from a superluminal region of space into a subluminal region of space, and so it can start making progress towards us. So we can detect it, so we can see that distant galaxy, which is of course now even further beyond our Hubble sphere, but we can see its light. We can detect that it's there. This is remarkable. In fact, all of the photons we now receive from the first 5 billion years of the universe, they were all emitted in regions of space that were traveling at the time faster than the speed of light relative to us. The objects that emitted them were, are, and always have been moving away from us faster than the speed of light. But their light has entered our Hubble sphere and had enough time to reach us, and so we can see them. So the observable universe is larger than our Hubble sphere. It's actually limited by what's called the particle horizon. That is based on the amount of time light has had to travel towards us since the beginning of time. That is 13.8 billion years ago, as far as we can tell. Now, because the universe has been expanding and that expansion has been accelerating, things are much further out than 13.8 billion light years away. I mean, the observable universe has a radius of over 46 billion light years. The diameter is about 93 billion light years. That is a huge volume of things that we can see. And 13.8 billion years ago, everything in that volume and everything beyond it that we can't see would have been compressed into a tiny, infinitesimally small point that we call the singularity. Actually, no. I mean, that would be true if the universe is finite, but if the universe is infinite, and it kind of looks like it is, then it was always infinite. So the Big Bang would have happened literally everywhere. But if the universe has always been infinite, then what is it expanding into? Well, it doesn't have to expand into anything. I mean, it can expand into itself. That's the thing about infinity. You never run out of it.
Okay, so hopefully that just shows you some kind of mind-bending stuff about talking about the universe. So just sort of a fun way to start the universe, lots of questions, and I'll be candid and say they have questions that I can't always answer. So it is a fun way to start though. And you'll find that there are students that have geeked out on this and they might know things that you don't know or I don't know. So that is great though. But I want to zoom out. So I just wanted to kind of give you that dive in. And actually I didn't see here to bring some coherence to you. I want to kind of teacher talk for a moment. So let's go back out. Actually, I'm going to go all the way back out to the agenda and just say, so let's zoom out on this whole thing. So largely there's one communal whole class thing that we do. That's station 0, because it's not really a station. That's why we gave it station 0. So that's a whole class thing that we'll talk about in just a second. And then there's really 10 stations, and it takes 2 days to get through. They'll only get through 5 stations or so a day. Maybe, yeah, roughly 5. because there is some whole class stuff, but that's the joy of bite-sized learning, that they're going through the stations, which also additionally allows you to be the guide on the side. Those stations are largely self-sufficient. People have used this on a sub day. I do think when you come back, you're going to have a lot of questions that have been generated and maybe didn't get answered, but that really allows you to walk from group to group, check in with them, and have some really fun side conversations that, someone's really interested or weirded out by something. And then, as we said before, has some really neat, inspiring awe. And just to call it out again, that cross-cutting concept of scale, right? You can just see it popping out every time you talk about the universe compared to the Earth, and you'll see stations there's some stations that are targeting just that. Okay, before we dive in, I'll just check in with Matt and see if there's any broad stroke sort of comments to say before we talk about Station 0 and then an overview of each station.
No, I think that's good, and I think it's important to know, like, we're going to talk about Station 0 here, that all of these stations are built up around some aspect of explaining that the NGSS statement of like constructing explanation of the Big Bang based off of astronomical evidence, light spectra, and composition of matter. And so that is, each of these stations was chosen to reveal some aspect of that. And the first station is a way to give some data for students to look at of this. So this first station actually, there should be one more slide. Yeah, so the worksheet looks like this, and we'll come back to this quite a bit, but what is our universe and what do we see happening in it? And so all of the stations, if you've done the stations from, for example, the sound stations, has a watch and draw, some sort of response, something else. And this one has a data table that they're going to complete. If you go to the next slide. This one. So and this is these are stations with the galaxies that are from a variety of different distances away. So Milky Way, Pinwheel Galaxy, and these are kind of like cards that are put up, and we'll show you a map. They're either put up around a classroom or preferably to inspire some of the awe around a football field. So there's a classroom version and there's a football field version, and these are intentionally placed at positions that are certain distances away from the center. So our center, when we are looking out in the universe, is from Milky Way, and you can see these are laid on top, and it's intentionally placed at certain positions along the way, and students are going to measure and convert from the scale model that's either on a football field or the classroom tape measure to an actual distance. Each of the cards has the picture of the situation, but also has some more information on the backside. If you click there and go to like the next. So it's what it looks like how bright it is, but also has this idea of the redshift and how fast is that galaxy moving away from us, and it tells the relative velocity of that. Now, of course, students haven't heard about redshift yet. They don't know what that means. There's a station on that. They don't know how we can say the actual versus observed brightness. There's a station on that. So this is all data of how far away are they? That's found from the brightness of supernovae. And then how fast they're moving away. And this leads us into station 1, which is I'll leave for Bradford to talk about.
Sure, thank you. Yep. And maybe just to, yep. And I'll just say this too, from there's 3 videos that we start with, and we saw that one. But one thing that's surprising to students is as you zoom out, right, it feels like our solar system is the whole universe. And of course, you can zoom past that and you see the galaxy is the whole universe. And then there's some videos that even show multiple galaxies. So it feels like the universe is really clumpy. And of course, one of the videos zooms out really far and shows, you know, on certain scales, the universe feels clumpy, right? Like there's the Earth and then a 250,000 miles until you get to just the moon. And then the next thing, you know, Venus or Mars, they are so far away. But when you zoom out on the universe, it is pretty even. So that's just a piece there that is in those videos. And I'll jump into the handoff from Matt. Okay, so they got that data on actual distance. So they're measuring, they're out there with a tape measure, measuring with a tape measure. And it's really fun. I actually did do this one this year. Matt mentioned he was out, so I had I got ahead of everyone, so I had a couple extra days. So I did this unit, and or you know, it was really small, but really fun. I had to do it it was rainy, so we did it in the classroom, but it was super fun. And one of them was in the hallway. So, yep. So they go, and we of course want them to notice that relationship between the distance and velocity, and of course, help find Hubble's law for themselves. Okay, I'm gonna close out. Yeah, I'm gonna close that one now. And a nice little piece of this is they plot it, they find the relationship, and then we have them read just a excerpt from the original article. It's actually one of the more readable articles by Hubble. And yeah, so just a great piece. And yeah, that's the level, that's the broad stroke. You kind of get the idea that there is a bit.ly, they go and graph this and find Hubble's law. I'm gonna close that. Okay, and now
So,
we're gonna,
yeah.
oh yeah, go.
In
Yep.
that station, they're looking at, you know, how does distance away of a galaxy affect the velocity? And that's pretty surprising that just because something's further away, it's moving faster. And so, you know, so what does that mean? Like, why is that? You know, scientists believe the universe is expanding. What does that mean? And so this is station 2. And we have a short minute physics video on that. There's some other resources that we'll probably not show, but I think the video, it does do a pretty good job of giving a brief overview. And Bradford, if you want to show that one.
Yeah.
I don't know
Yep.
how long.
Yeah. I think we're pretty good. Yep. So we'll have to be careful on the time, but yeah.
Yeah, just a minute.
The universe is expanding, so does that mean there's a center from which everything is stretching outwards? I mean, it looks like the center is here because this point didn't move when we scaled, but we could just as easily have watched the scaling from this star or this one, and they each look like the center. In fact, anytime you scale anything up or down, there's no real center to the scaling. I mean, this square was clearly scaled up from its center. I mean, its corner. I mean, that point over there. The point is, sure, there may be points that stay in the same place because of your frame of reference, which is why it appears to us as if the Earth is the center of the expansion of the universe. But to someone in the Andromeda galaxy, it would appear that they were the center of the expansion. In short, if you're too close-minded to view the universe from different perspectives, it's easy to think you're at the center of the universe. Maybe that's the universe's way of making us all feel special, but really, we're not.
So this has just a quick video, but there's a couple of activities that we have them do with that. So one of them is a simulation that they can play around with this expansion. Another one, they take rubber bands and actually stretch them out and see how different pieces on there could be moving away from each other. And so looking at that expansion and looking at it in lots of ways. So you know, how does that expansion happen? It's and it's shown both videos and through some hands-on activities as well. And that leads us to our next question, which is our station 3.
Yeah, so people are familiar with it already. You know, how does a car horn inform us about the movement of galaxies? And that is a reference to the Doppler effect. And we will actually have a couple stations that deal with the Doppler effect. Yep. So a light touch on this one. Obviously, it'll take some time, but maybe here's also good. You can just imagine that if you're in front of a moving source, the waves get piled up. If you're behind the moving source, the waves seemingly get spread out. And it's good. Students, those visuals, there's some videos, multiple stations. And so that is the how does a car horn help us? And then, of course, they make a connection that galaxies are moving away from us. So we see that same thing, that the wave crests seemingly spread out. The waves seem to be longer. So there's that one. And then stepping away from that, if every direction you look, there's a star, or really there's basically every direction you look, there's actually a galaxy. Why is the sky dark then? That seems like if you see darkness, your intuition says there's not a galaxy there. So we're not going to watch it, but there is an activity and a video, and somehow I must have closed it by accident. So I got messed up. I'm looking for, with all these stars, the galaxy, why is it dark at night? 4.
Yeah, a tab up is.
Yeah, oh, it's right here. Okay. But anyways, another Minute Physics that does a great job, and really good job, and has, again, with all of those videos, we try to have some hands-on things whenever possible. So this is in the supply list, these spectral glasses. Really cool. So there's a couple options there. And again, just another little great feed in to chemistry, that if you have the gas tubes, you don't need them. Fluorescent light, sunlight works really great. Phones to look. But anyways, just connecting the spectral lines of the EM spectrum and the visible spectrum, and understanding why, if there's galaxies everywhere, does the night sky end up dark. With that, I'll hand it over to Matt.
Yeah, so our 5th station, what direction would you look at to see the Big Bang? This one has a physics scroll video associated with it, and is looking at, oh, yeah, it's that one, Bradford. Yep, it's looking at cosmic background radiation. There's like a 3D image of the signal that's in the background, and that's one that kind of gives a good background on what's going on with where are we going to look in the universe. And so just another nice connection to the Big Bang, using some cool resources that we found.
Yep. And you can kind of see there is a nice order if someone started at station 1, but usually students need a few times. So even when you don't start at 1, it usually takes a station or two to figure some of this out. I think I closed the tab, so I'm kind of off by 1. So, but we wanted to each always go back to here. So station 6, how do we measure how far a star is, right? Remember when we started this, we told them how far the star was. They measured with tape, so they kind of got the data collection experience, but had to convert that to the scale factor to find the actual distance. So now in station 6, they are actually getting the background. How do we find that? And there's an excellent NOVA video. Gosh, sorry, I closed that.
It's slide 39. Just go to.
Yeah, thank you. So I'll go back to it. And yeah, there's a little bit of sleuthing because this was freely available, and then NOVA took it down. But now we found NOVA has a couple different ways they put out videos. And so anyway, long story short, we did find that PBS Learning Media doesn't take down their video clips. So we know we'll have this one forever. Good. So I'm going to full screen. It is 5 minutes, but it is excellent. So we'll time check though. Okay. Yep. That's going to.
1A supernovae. It's like the universe's free gift to us. Because they all explode in the same way, they reach pretty much the same brightness. So if you see one dimmer than the other, it means it's further away. And that allows us to measure distance to the galaxy that's hosting this supernovae explosion.
We have seen type 1a supernovae across the entire universe. We can measure the distance to their home galaxies. And that can tell us how the universe is changing over time.
So when we look at distant supernovae, we see something really interesting. Their light's not just dimmer, it's redder. And the further away they are, the redder their light is. But as the light travels from this distant galaxy to us, space itself is stretching. And so the light gets stretched along the way, it gets redder. And this is called redshift.
We see the effect of redshift in the light from every distant galaxy. And that means space is stretching everywhere.
And that means something truly amazing. It means our universe is expanding.
By studying how galaxies themselves are redshifted, we have known for nearly a century that the universe is expanding. But by using type 1a supernovae to study it in detail, we can accurately tell how fast our universe is growing. And what scientists find is something completely unexpected.
Astronomers working with the Hubble Space Telescope started to realize that the universe is not just expanding, but it's actually expanding at an ever increasing rate.
It's that accelerated or speeding up stretching that really did catch our community by surprise.
We know the universe is expanding. And thanks to Hubble, we have evidence that this expansion is accelerating over time.
So if you know the universe is expanding, you can just do a thought experiment and turn time backward and know that the universe was smaller in the past.
We can wind back the clock through thousands of billions of yesterdays. Back to a time before our Earth and Sun. To a time before the first galaxies. And finally, we can cross the cosmic dark ages to pinpoint the moment the universe began. A moment we know happened 13.8 billion years ago. The Big Bang. The moment when our universe burst into existence. Yet it wasn't anything like an explosion.
This is the initial state of the universe, which was very hot and very, very dense.
Everything, the whole universe, was held together in a very tiny region of space.
So everywhere in the universe is almost like being inside of a star.
All the matter that has ever been produced came from that moment in time.
Excellent. So, it's precious time to show that video in the webinar, but that was key to show almost all of that. Because again, remember that early universe is like the inside of a star. That's going to be really important to one of the hardest last little pieces of what's called for in the performance expectation and the evidence statements. So the composition of matter in the universe. And that's a key thing to realize that, and they want a very technical detail there. So actually, I want to okay, we are close on time. So again, that video and hopefully you saw how it also talked about the Doppler effect, right? Those farther ones being further away. You heard that stretching of space. And again, I'll just flash this up, right? The stretching of the rubber band and stretching of space and the car horn. So just want to show you that students don't have to learn every little detail from every station. There are multiple overlapping spiral nature. And students need that. There is so much going on there. And of course, if you're walking around and talking with them, that's another touch, right? They need multiple touches on each of these. All right, with that said, how do we see the invisible? And of course, that's a little bit of a reference to the Webb telescope that sees in the infrared. And with the Webb telescope, gaining, just awesome pictures coming from it, and students, some of them that have an interest in astronomy are asking about those questions outside of the curriculum in the classroom. So that's a great resource, but also, just talking about current events. So Station 7 gives us that chance. Really, I'm so tempted to show all these videos. Well, and please do keep sharing videos. We have a lot of great ones, but you can never have too many astronomy videos. Teachers are always asking for videos, and we have like a study hall period where I just show science videos if we're all caught up on everything. But in any case, here is a station that looks at the infrared and the Webb telescope and seeing the formation of early universes, and lots of neat, seeing galaxies swallow up and combine with other smaller galaxies nearby. Oh my gosh, we didn't even talk about that, but back in Halley's Comet, we end that task with some of the simulations and pictures that the Milky Way and the Andromeda galaxy are likely on a collision course and will merge into, I'm forgetting the name of some clever Melkdromeda, just some clever name where you combine Milky Way and Andromeda. So those two are on a collision course, and the Milky Way has already swallowed up several small galaxies, and that's one of the things that gave us our spiral arms. Okay, so this video hints, or not even hints, shows some of that, but that is how do you see the invisible? And I'll hand it over to Matt to talk about Station 8. How big is the universe?
Yeah, so just kind of reiterating that lots of these stations are hitting on those same ideas, like and also coming back to our waves unit, like talking about infrared, looking at that stretched light. This next one, how big is the universe? Does a good job, has a video with it. There's just trying to give a sense of scale of the universe. And so part of their task is to calculate, if the moon is one step away, how far away is Mars, how far away is the sun. And then there's a couple of really cool just graphics just showing the scale of the universe. So there's this one that just goes through a bunch of celestial bodies, and then all the way to the size of the universe. And then there's another one that basically says, like, if the moon were only 1 pixel, how far away would things be? And so when students click on that, they scroll out and just see how far away things are here. So they're just a couple just interactives that students can look at and do and play with before they are looking at just the sense of scale of the universe. And that leads us to our second to last station, Station 9, and I'll leave it to Bradford to talk about what is the universe made of.
Okay, this is that heavy hitting one. There, I mean, this is straight out of the evidence statements. Yeah, I'll just say that it is challenging for students, but that is what our universe made out of. And one nice thing is a lot of, especially early universe, hydrogen and helium. And we heard in one of those videos how the early universe was a lot like the sun. But I'm just going to highlight this, and you definitely got to read this. They're in the teacher calendar. There's a background reading from National Geographic. I actually do think I learned this back in college, but I had to reread it. That evidence statements once specifically for them to call out the ratio of 75% hydrogen to 25% helium. And so that this does give some explanation for it. And I do want to just show something to make sure people know that this is there. So here's that task goal. And actually we're trying to we have revised several of the teacher calendars. So it's always great to get that feedback from people. The functionality, lots of times that I never knew that was there. And if you look right here, here is that performance expectation, construct the explanation. You can get to the evidence statements. Every one of these is true. So if I click on the performance expectation, that'll open up, well, I guess actually technically this takes me to nextgen.org, who put together the performance expectations, the NGSS from the framework. And then I guess it's a second click, relevant evidence statement. So you do got to click on that. And then there is the long explanation of, what are the observable features of student performance by the end of the course for that performance expectation. And I'll just say, here you see the ratio of hydrogen to helium, again, the hydrogen to helium and the stars and interstellar gases. So one, just want to show you that we are tuned in to the evidence statements, even beyond just the more overarching language of the performance expectation. All right, so again, that is why this detailed slide is in there, and it does work pretty well. But yeah, just want to call that out. And students or teachers have asked, why is that in there? And that, I think, hopefully gives that explanation. And so you got this visual history of our universe, and of course there's another little fun application extension that generates a lot of questions about dark energy there. And that also connects back to unit or the Halley's Comet task. So you can see these things do build on each other, and students see that connection. So sorry, when I try to get back to the worksheet here. All right, so that is what is the universe made of? And an important piece of that is that ratio of hydrogen to helium. Maybe it's just worth saying the upshot that if it was like the inside of a star, you'd expect the fusion to happen, and it did happen. However, you kind of think with high energy, super high energy, sometimes the early universe was hotter than stars, so you should have massive fusion. But actually, because it was so hot, those atoms got hit and broke apart again. So actually, that temperature ended up being, I'm not going to explain all of it, but it is in the it's a simplified version is there for students. And then just to tell you again, on the teacher calendar, here is a great article that gives some background on that. So that's right there for you in the teacher calendar when you have a little bit more time. But that wraps up from the student side of things, them getting what is the universe made of the composition. And then a fun one, and obviously a current event is what is at the center of our galaxy. And how cool is it that, just really in the last couple of years, an actual image of the black hole or the surrounding area of the black hole. And of course, with the movie Interstellar, there's some amazing computer generated images of black holes, and just a really fun, really generates a lot of questions. And there's some great videos on that in there. But again, if you have other good videos, teachers are always asking for even more videos. So if you have them, it would be great to be able to share them. All right, so to bring it back, that wraps up our 10 stations. And so I'm going to go back to the agenda. And really after that, then there's a synthesis discussion. There are slides for this task. And I keep thinking I'm on the teacher website, but I'm on the agenda right now within the teacher website. So, but in any case, since I am here and I don't want to click away and then click back too many times, here, they're, really in the last like year, but the articles that have been written about it are kind of the last couple of weeks even, is that it doesn't mean that everything that was said is wrong, but dark energy might not be constant. That acceleration might not be exactly what they assumed. They assumed it would be constant, and it might not be constant. So that is cutting edge current astrophysics that is in the realm. This article is written in a way that is approachable for high school students. I'm about to throw it over to Matt to just kind of see if I'm going to try to wrap it up, but it's good to get multiple perspectives. Do you want to just hammer one more time? Scale, right? Like there was just multiple times when we were looking at the scale of objects in our universe. And I tried to show that kind of quickly on screen while Matt was talking. And then the distances from the Earth to the moon, the Earth to the sun, the sun to the center of the galaxy, just so good, loaded with opportunities. But then after all of those stations, and then here's that slide deck that I was talking about, there's some whole class synthesis that you can go, and ultimately we want students to construct an explanation for the Big Bang based on astronomical evidence of light spectra, right? How do we see the invisible? And that Doppler shift, the motion of galaxies, which again, Doppler shift is relevant there, and that type, the supernova as a standard candle. We know roughly how bright they are because of the way that type of star goes supernova. It's almost always at the near same mass, so it has about the same energy when it explodes, so it's about the same brightness. And so motion of distant galaxies we can figure out, and then as I was just summarizing recently, the composition of matter. So they got to put those together in a CER to explain the Big Bang Theory. I know I talked quite a bit there, so I'll give Matt just a chance to reiterate and mention anything that I missed.
Yeah, so in that document that we were showing, kind of going back and forth between, after they've gone to the station, all those stations, they have lots of evidence to kind of cite and show. We have them do Stronger Clear, which is a protocol we use to have students talk and try to both improve and actively listen to somebody else speaking. And then we have some writing for them to like try to pull all of the information together, everything that they've learned as they are pulling that together. Again, these 3 different activities are modular. They could be done together, they could be done separately. There is some other asynchronous activities that are there as well, just to give students extra reps at that. One thing I wanted to do before we're close to ending here is just one last time, I just put in the chat the educator sign in. Most of you have already done that, but if you weren't able to do that, please be sure to click on that link. Yeah, any last things, Bradford, or?
Yeah, seems like a good time. We'll actually end a couple minutes early, but so with that though, we'll close up the meeting and got a question or just something that didn't fit into the webinar time. We'll hang out for a couple minutes here and glad to connect. So we'll end the recording and